Okay, so today we're going to be talking about the first part of our analysis for Group 1. To the left, we have our data that we were given, and this is what we're going to be discussing throughout this show. So basically what we have is that we have different types of variables. We have the number of centers, which we have 24 sample sizes, the type of centers, which PC stands for private church, NPC is non-church affiliated, and PV is public facility. We also have our late fees and our no late fees, and our overall purpose of this research project is to see if the late fee policy affects the share of late parents and how.
First, we need to figure out what we should use to figure out the data. These are the requirements for the hypothesis t-test. The first requirement is we have two sample means from the same subject. Each sample is continuous. They are dependent of one another, and they can be paired with the opposite sample, which is an inherent relationship. The match pairs are simple random samples, and our last requirement is the sample size must be larger than 30. And in the last slide, it showed that there are only 24 samples in our data, so we have to do the alternative requirement, which is to see if it has a normal distribution.
So for this, we're actually going to be focusing on the differences between the late fee and the no late fee. And we're going to have to conduct a few different types of tests to prove that our differences actually appear to have a normal distribution.
To figure out if it has a normal distribution, we're going to do the Shapiro-Wilk normality test, which tests the difference with our critical value. In the figure, you can see that our p-value is 0.61 and our critical value is 0.1, so our p-value is greater than our critical value, which means we would fail to reject the null hypothesis, and there is sufficient evidence to support the claim that the sample mean difference appears to have a normal distribution.
So to kind of further support the test before, we did a linear or scatter plot graph, and you can see that the majority of our data falls within the line with the exception of 3 outliers, and that we have a higher correlation, which can conclude to a normal distribution.
And this is our hypothesis t-test, and for our null, there's a normal distribution of differences of the sample means, and our alternative is there's not a normal distribution in the difference of the sample means. Our t-stat's negative 9.55, and we have a p-value of 0.001 with a critical value of 0.1, and which means our p-value is greater or less than our critical value.
Okay, so now that we've concluded that we have a normal distribution within our differences, we can now test whether or not they affect the share of the late fee parents. So in our final analysis, where we tested the claim that the late fee policy does not have an effect on the late parents, we concluded that we would reject our original claim, considering that our p-value of less than 1 was way less than our critical value of 0.1. So in this case, we'll be supporting our alternative hypothesis is that the late fee policy does have an effect on the share of the late parents.
All right, so now we're going to be talking about our second part of our data analysis. So we have our population data with our certain criteria of living status, household income, geographic region of residence, age, children under 18, number of visits to an art museum, books owned, and personal art ownership. Our dependent variable in this data set is right here, our art museum visits. It's dependent on all these other variables here listed, and those are the independent variables. These independent variables can help determine and affect the total attendance to a certain museum. This data is relevant and necessary for our institutions in the United States because they can analyze the population data and mark it towards the best population to yield the best attendance. Since we are given one dependent variable with 2 or more independent variables, which in this case are 7, we must by definition use a multiple linear regression model. For this model, the proposed research question is find the best linear model to predict the number of visits to an art museum using any or all of the other variables. Before we begin the regression, it must follow 3 requirements. The sample data is a simple random sample of quantitative data. Each pair of data has a bivariate normal distribution. Random errors associated with the regression equation are independent and normally distributed with a mean of 0 and standard deviation sigma. This data appears to follow each of the 3 through using a residual plot, and there are 3 guidelines to carry out the test now that we've confirmed it meets the requirements. The first 2 are using common sense and practical considerations to include or exclude variables and considering the p-value for the test of overall model significance. We will use the 3rd guideline later. Here are our hypotheses by below. We got our null hypothesis, which is all the independent variables equivalent to 0 and equivalent to each other, meaning the model is not significant. And an alternative hypothesis, H1, at least one of these means is not equal to 0. It would mean that our model is significant. Now we must identify our test statistic of f-stat and our p-value. They're listed here, 88.15 and 0.0001. From our analysis of the variance table here, our p-value is less than our significance value of 0.05 alpha. Therefore, we reject the null hypothesis and formally conclude that our model is significant. We can now continue with our test and trust our model. Our third guideline, considering equations with high values of adjusted R2 and low p-values, and including only a few variables, we can look at these figures 3 through 7. They list all the possible combinations, and through that we yield the 3 best candidates, which are listed here, through figure 8, and 9, and 10. Now after doing so, with the age, books, living status, age, and books, and age, children under 18, and books combination, we can yield that our best regression equation through our parameter estimates, our t-stats shown below, and through our comparisons is this right here. Our var 6 plus these numbers, var 4, var 7, which is age and books for the variables.
In conclusion, through our findings, our StatCrunch data and theoretical calculation above prove that our regression model is the best linear fit from the equations given. We don't have any objections to our regression model for 3 reasons. First, our regression equation follows the 3 requirements for being a good linear model. Second, our regression equation gives us a positive museum visits value that is within the range of our data. And third, in our analysis of variance of figure 2, our p-value is less than alpha 0.05. This rejects the null hypothesis and gives us reason to conclude our model is significant. These 3 reasons give us certainty that our model is the best linear fit for a multiple linear regression model. We found that the best predictor variables, age and books, that help to determine our response variable, which is annual museum visits. There are a few issues with the data. First, much of the data is presented nominally instead of quantitatively. For example, household income is recorded as 1, 2, 3, 4, and 5 for various income ranges. Geographic region of residence is also recorded nominally as 1, 2, 3, and 4, and individual owns art is recorded as 1 equals yes, 2 equals no. Since all of those variables are recorded as nominal data, they aren't significant. And so since over half of the given variables are nominal instead of quantitative, the analysis can be significantly improved by including more variables that are recorded quantitatively. After analysis, the best linear regression includes var 4, which is age, and var 7, which is number of books read in the past year, both of which are recorded quantitatively instead of nominally. One thing that we could do to improve the posed research question is to take a poll asking how often people visit our museums from a sufficient sample size. That data could be used in conjunction with the multiple linear regression equation in order to make an even better prediction for the number of visits to an art museum. This concludes our presentation.